Xpresso is a node-based programming language that allows you to dynamically link dependencies between object properties. Select the cube object. Navigate to Coordinates tab and right-click on the Y-axis. On the pop-up menu, select Expressions and choose Add Driver. This specifies that we will be using the position on the Y-axis of our cube to control properties of other objects. Select the sphere. Right-click on the Z-axis and navigate to Xpresso and choose Set Driven. Select the cube and move it on its Y-axis. Your sphere should automatically change its position on the Z-axis. Note that if you select the sphere and attempt to manually change the position, it will immediately switch back to its original value. This is because the value is being entirely driven by the driver. In your Object Manager, to the right of the sphere object, you should see a new tag. This is an Xpresso tag. By right-clicking and establishing which parameters will be the controller and which ones will be controlled, we've set up our first Xpresso expression. We've linked one property to another. If you ever forget which expressions you've defined, select the Xpresso tag and check the Attributes Manager. Its default name will describe which properties you've mapped to one another. If you will delete the tag, your sphere will become an independent object. Select the sphere object. Navigate to Coordinates tab. Right-click on Position Y and choose Expressions. Set Driver. Select the cube and right-click on Position Y. Navigate to Expressions. And now select Relative instead of Absolute. As you can see, the relative mode has not changed the default position of the cube object. We can link that property to as many other objects as we want, as well as use more complex calculations than just a one-to-one link. Many beginner users find Xpresso intimidating, but creating basic functions is simple and can save you a lot of time. To create a new expression in the Object Manager, select the desired object and choose Tags. Cinema 4D Tags. Xpresso. This action will automatically fire up the Xpresso window, which is divided into three main areas: Xpool, Xmanager, and the Xpresso editor. You can close the editor at any time and reopen it by double-clicking the tag. The Xpresso tag can be viewed as a container in which our expressions are housed. In most cases, it doesn't matter which object has the Xpresso tag assigned to it. The Xpool tab contains all nodes organized by class and then by group. You can drag and drop the desired node directly to the Xpresso editor. Alternatively, we can right-click on the Xpresso editor's Xgroup field to display this list of available nodes. The Xmanager tab displays a list of all nodes contained in our Xgroup. You can navigate the contents of Xpresso Editor's Xgroup field in a similar way to the Cinema 4D viewport. Nodes are the primary building blocks of expressions and are designed to carry out the most diverse of tasks, from reporting an object's current position to processing math operations. A node's parameters are displayed in the Attribute Manager. Each node represents an object in the scene and is referred to the object where an Xpresso tag is attached to. You can drag and drop another object to the reference field. Or directly onto the object node. In this case, it makes no difference which object has been assigned the Xpresso tag. Nodes have input and output ports that can be used to exchange data between nodes. One click on the blue field opens a list with the existing entries of the node. The red field stands for the outputs. Alternatively, you can drag any parameter from Attribute Manager and attach it to the respective node. To enable nodes to pass values to one another, you must first create the necessary ports and connect those ports using wires. To create a wire between two ports, drag the circle of one port and drop it onto the other. You can delete wires from the port's context menu or by clicking on them. Also, you can delete ports by double-clicking on them or from the context menu. You can minimize or maximize a node by double-clicking its title bar. You can drag a corner of the node and change its size. Hold down the Control key and optimize the size by double-clicking on the appropriate node. If we take a look at the Attribute Manager, we can see the object's various parameters. If we were to output the data from these parameters via an object node, we would have to ask ourselves, in which format will this data be output? Each node has a data type that defines the type of value it uses. Navigate to the Xpool field. Click on the search icon and search for the constant node. Drag and drop the search result to the Xpresso editor. This node enables you to generate constant values and pass them to other nodes. You can enter the value and set its data type in the Attribute Manager. To display port's data type, hover the mouse pointer over the port, and Cinema 4D will provide information about the data type. Alternatively, you can see more information about the port from its context menu. The integer data type supports whole numbers that can be negative, 0, or positive. Numbers after a decimal point will be ignored. This can lead to inaccurate results if fractions are involved. You can use Remark node to document your expression with explanatory notes. Type the note into the Attribute Manager's Remark field. Hold down the Control key and move the node to create its duplicate. Unlike integers, reals can be fractional numbers. A typical example of a real is pi. Use the real type when complex calculations are involved and you want an accurate result. If you connect two nodes that use different data types, the wire between the nodes converts the data type automatically if the types are compatible. For example, if a constant node passes a real value of 3.4 to a subdivision input whose data type is set to integer, the value will be converted to an integer automatically, in this case, to 3. You can see the automatic conversions when hovering over the line. The bool data type has two possible states, true or false. Although you can use bool values in math calculations, keep in mind that the bool data type is able to hold only a value of 0 or a value of 1. The vector data type can be used for manipulating object positions, HPB angles, any type of colors, and point coordinates. In Cinema 4D, a vector always has 3 components. When converting a vector to an integer or a real, the length of the vector is calculated automatically. On the other hand, when an integer or a real is converted to a vector, the value is used for the vector's x, y, and z components. A matrix is a group of vectors, such as an object's global matrix, that contains the object's position vector and 3 vectors for each object axis. The axis vectors represent not only the direction of the object, but also its scale. The scale is defined by the length of each axis vector. Therefore, the global matrix gives you access to the object's position, scale, and rotation. The string data type can hold letters, numbers, and special characters. Xpresso wires are able to automatically convert numeric sequences in the string. Drag and drop the cube into the Xpresso editor and create its duplicate. Select the red field of the first node. Navigate to the object properties. Size Y. Draw a line from the size Y output port to the blue field of the second node. Navigate to coordinates. Position Y. Right now, our cube's parameters directly link to one another. If we will change the size of our cube, the position will also be changed. But what if we want those values to still be linked, but not always equal to one another? We can pass the value through the math node, which performs math operations. Addition is the default function which adds the inputs together and outputs the result. You can add more inputs from the blue field. We can use the result node that allows us to view the result of our calculations. This node displays the input port's value. This lets you check if the value is correct. The type of value can be changed in the attribute manager. Now let's change the function to divide. Connect the output of the cube node to the first input of our math node. This specifies that we will be using the size of our cube to control first input of math node. If we will check the attributes manager of our math node, we will find only the second input. This is because the first input is being entirely driven by the cube node. Connect the output port of the math node to the input of the cube. Now, This node will send the size value of our cube to the math node. The value will be divided by 2, and the result will be sent to the position input of the cube. In computing, the modulo operation finds the remainder after the division of one number by another. For example, this expression would evaluate to 1 because 5 divided by 2 leaves a quotient of 2 and a remainder of 1, while 9 and 3 would evaluate to 0 because the division of 9 by 3 has a quotient of 3 and leaves a remainder of 0. In formal language theory and computer programming, string concatenation is the operation of joining character strings. For example, the concatenation of snow and ball is snowball. If we will concatenate the number 5 and number 2, the result will be 52. Let's change the data type of the result node to real. If we will concatenate letter P and letter I, the result will be the number pi, which is a mathematical constant, the ratio of a circle's circumference to its diameter, commonly approximated as 3.142. If we will change the data type back to string, the result will be a string value of pi. Let's create a simple clock. At first, we have to create a math node, which will calculate the seconds. Change the data type to integer, function to modulo, and set the value of the second input to 60. We can use the project time as a first input. The output of project time is affected by the frame rate. If the rate is 30 frames per second, the time value for frame 30 is 1 second exactly. And after every 60 seconds, the calculation will start from 0. Let's duplicate this math node and set its function to divide. This will define the minutes of our clock. Finally, we can concatenate these values and see the result of our calculations.